today I will just completely devote most of the lecture to answer questions on the whole homework. So that's one. Number two is try to practice problem. And based on the feedback that you gave me, I threw in a few more just to give you a chance to work them out. And again, the solution posted for the practice problem, so you should be all set. Okay, so agenda for today, I didn't finish completely the minor losses. I'll take maybe 10 minutes to go through that, plus an example that is taken up in the text. Then I'm going to spend 10 minutes on the review for test 2, which I've posted, both of those on tablets, so you don't have to copy anything, you just pay attention. And then whatever time left, I want to answer all the questions regarding the homework in chapter 8, and there are a couple that I want to bring out to your attention for various reasons, and I will start with those, and then after that, it's open for Q&A. If you have no question, it's to your benefit to slow me down, but if you have nothing, then at the end of the lecture, I would go for another example, which I had meant to do regarding Bernoulli, but it just never have the time to go through that. It has to do with water jet. Try to describe a water hose, the trajectory, how it behaves, and so on and so forth. So your responsibility is the end of this lecture. All right? So practice problem, test 2, reading is just a repeat, nothing new, nothing new. So with that, let me go back to look at some of the elements of what we call the minor losses. And the content here are mostly taken from the textbook. So we talk about minor losses, we talk about valves. So here are some examples of the valves people use in industry. And some of these happen to be used in our wind tunnel here at Virginia Tech. The one here at the bottom is called butterfly valve. So you have a pipe, 7-inch diameter, just like the one we work on pumping gasoline. To control the flow, Q, the velocity, you basically create a blockage. So a butterfly valve is a circular disc. All right? If it's in line with the flow direction, then the flow is completely blocked. You have zero velocity, zero Q. If it's fully open by 90 degrees, kind of like this, then you have the minimum blockage, and you have the maximum velocity, the maximum Q. And in industry, petroleum, processing, paper mill, this kind of power plant, this kind of valve is used quite routinely. And in our wind tunnel, what we do is we control this valve with a very fast actuator that can produce thousands of pounds in a matter of fraction of a second. And the reason is we have wind tunnel that's very high pressure, like 200, 400 psi, and we have to open the valve, set it in the right position, and let the air in the tank, it's a storage tank, pretty big, blow down, so then in a matter of 10 seconds or 20 seconds, we can establish a quasi-steady-state experiment. We call it a blowdown test. And what we do is to simulate the condition using similitude of a gas turbine engine up on the hallway. So we have high-speed flow, Mach number more than 1, matching the Reynolds number. And we do experiment on that. So this is called a butterfly valve. Very common. Another example that will help to illustrate all that valve and how they create losses is in here called gauge valve. Gauge valve is another circular disc, but it doesn't rotate along the axis and create blockage. Instead, it basically manually turns a mechanism here that allows the gauge valve to go up and down. Instead of rotation, it goes up and down. So when it's fully open, you have the maximum velocity. When it's fully sit down at the bottom, no flow. So different combination, different position of the valve will give you different losses, the K, and that's how it comes about. So the manufacturer of all of these will have to do tests. And from that, they give you the kind of table you use for your homework. So here's a gate valve, partially open, and then you have different value of K, the loss coefficient, depending on the position of the valve. Where it's fully open, it's basically very little losses on 2 or K, and that created due to some cavity in the valve that allowed the valve to open and close. When it's 3/4 closed, very much down, you have losses that way high, 20s plus. So as an engineer, if you are the customer who buy the valve, who design all this flow system, You can use this chart to determine how much pumping power you need for different flow rate throughout the power plant, because it's not always constant. All right? Even for our power plant, the steam power plant up the street, you don't always want the design condition. Sometimes you change the flow rate. Questions? Yes?
So the energy that is lost from flow separation,
Mhm.
like that, where does it go?
Oh, very good question. So in thermodynamics, you have deal with a control volume that involve a power plant that involve a valve. Do you in the steam power plant? Right?
I don't know
A
if
throttle of a steam power plant. Remember all that? This is thermodynamics now. This is not fluid mechanics. But since the question is asked, I thought it's a close, very good loop to go between fluid and thermal. What is the change of enthalpy going through a throttling valve like this? A valve. What is the change in H? You don't remember? H, no, energy. You don't remember? You have that, I'm pretty sure. It's midterm now in your thermal. You must have done control volume for a power plant or a plant that involves a throttling valve or a valve just like this, where the flow goes through. Well, yes?
Isn't it H equal for the enthalpy?
Absolutely. You have some hesitation, but there's no change in energy going through the valve because there's nothing that can happen. I'm not getting work out. H remains constant. So energy doesn't change. So what happened through the valve? What did you lose? What did you lose? Velocity? Not quite. Pressure? Thermodynamic now. I'm asking you thermodynamic. Heat? No. Still no. What had gone up through the valve? H is the same. Yeah? Entropy. Entropy. No entropy, the S, the one that you hated the most. Right? I mean, it's so abstract, you have no idea what it is. And you lose availability. Remember the example I gave you? I'm doing work, I'm working. Okay? All this energy is there, but you cannot get it back. Same with this valve, it's throttling valve. Energy is conserved, but I lose availability. And in doing that, I increase the entropy. The energy is there, but it's gone forever. You cannot recover it. That's second law. That's thermal. Okay? I don't get paid to teach thermal, but since you asked, I have to answer it. Okay, joke aside, you get a feel for how all these minor losses come about. So, that's the valve, and then there are turns. We asked that question, someone asked that question, you know, when I have a bend 90 degree, do I need to know the radius of the turn versus the diameter of the pipe? Absolutely, this is how you attack that. Absolute sharp turn is the worst. Just sharp 90 degree. A little bit of radius help a lot. Yes?
Are you going to give us these charts on the test?
Yes.
Okay.
All the K value will be either given or in terms of a chart that you can look up, and you don't have to put it on your formula sheet. Yes?
If we have the charts for the K value, how will we know the difference between threaded or planned?
Yeah, that's one of the homework problems. It's not clear sometimes, but as an engineer, which one will you pick just to be conservative?
Worst case.
You take the worst case. If it's not spelled out clearly enough in the homework, then take the highest K, just to be conservative, right? But again, for pumping, for power plant like this, you don't look for 1% accuracy. Moody diagram is not meant to be 1% accuracy. So all this is the ballpark estimate. When you're done, you're good to plus or minus 5% at best, right? And that's fine, that's all you needed. That's most of what application is in pumping and pipe flow for mechanical engineering, right? Okay, other questions? So what happened, and this is way beyond introductory fluid, it will be more like advanced fluid mechanics or graduate fluid mechanics. When flow go around a band with viscosity, just like anyone fish in the river, you know, it creates some vortices. So here when the flow go around 90 degrees, at the exit, at the inlet, you have non-uniform flow due to what? friction, which is boundary layer. Anytime you have that non-uniform going into a band, doesn't matter it's a 45-degree band or 90-degree band, and in the river you have all that all the time in the New River. At the exit of that band, two vortices, just like shown in here, two counter-rotating vortices will be created due to friction and the pressure differential around the band. And that's where losses is generated. So that circulating flow is energy loss. And so give me the geometry, looking at the chart, I can tell you what K would you get depending on the specific detail of the band. And that's what need to be accounted for minor losses. So question on that? Yes?
So the circular flow, the vortex, vorticity losses, are those, is that like a momentum loss or what?
It is a momentum loss because the kinetic energy associated with that swirling flow is, for practical purposes, gone. So in the turbine, like in the gas turbine engine, a lot of those components, the turbine, the compressor, had flow turning. And at the exit, the same thing happened. Those are losses. So the engineer trying to minimize it to make sure that they have most efficiency out of those components. All right. And the same phenomena is what you see in the fall, high windy day, in the tall building out of the dormitory. You know, you walk around the side of the building, you see some tree leaf swirling. Have you seen that? On a high windy day? Those tree leaves is nothing but a marker to tell you the flow at the foot of that building is creating vortices that go around and around. It's the same phenomena. Same phenomena you have at the beach. You stand on the edge of the sand with the water on your feet, maybe a foot. When the wave retreat, you feel that the sand on your foot is eroding. Ever have that? Remember that? Same phenomenon. It's due to viscous flow, fluid mechanics, creating vortices that erode the sand from your foot, from the river banks, and from where the fish hide, and so on and so forth. Those are all minor losses. Okay? Intake. The diagram of the PowerPoint is rather poor. But the very bottom chart here just show you for different shape intake, the most sophisticated one will be aircraft engine intake. They spend a lot of money and time to make sure it's as smooth as possible. So this is a barrel mouth shape type inlet here is where the K value is the least lower losses versus something that the intake is very sharp. We call the re-entry intake. So again, you have to tell me the specific geometry, and then I can, from the chart, tell you how much losses is due to the entrance or the exit flow. That's what we meant by minor losses. So that's just a few examples of how all those pieces add together. Mostly empirical. The manufacturer have to give you all this data, and you as an engineer will then sort it out and decide that these so-called minor losses, how much you need to prepare to overcome in addition to friction, like Moody. And the example we show you is by no means minor. It's just very deceiving. Sometimes that minor losses is actually more than the frictional losses. So this next example will also help illustrate that. It's directly from the textbook. Example 8.8, and it's nothing but household application of pumping water from the basement all the way to the second floor, which is 20 feet high, 10 foot per floor. So the municipal water supply in Blacksburg or your town in DC must make sure they have enough pressure to deliver water to wherever you live. Could be a 3-story building, 30 feet, could be a high-rise, right? So the municipal pressure normally is well over 150 psi and so forth. Yes?
So I know when you're calculating losses within a system, you have to take into account friction, so the length of the pipe you're using as well.
No. Let's ask that question one more time. I want to make sure everyone can hear it. Ask that one more time.
When you're calculating losses.
When you're calculating velocity, go on.
Losses.
No. This is a very important question for all. I'm just trying to use that to illustrate. Because velocity is dictated by what? Which equation dictate velocity? You got it. Friction has nothing to do with velocity.
Right. I wasn't asking specifically about velocity. I was just
Okay.
asking about when you are looking at losses through a system,
Okay,
and you're looking at friction and frictional losses and minor losses.
okay.
Do you have to include the actual the length that is in the 90-degree?
In the minor losses component,
Yeah.
the answer is no. And this example will illustrate that. Because it happens such a short, the question is, when I do a minor losses like the intake or a valve or a band, do I have to account for the length of that band or the valve? The answer is no, because that's such a short distance. And over those devices, force separation, not friction, not shear, is what drive the losses and the pressure drop to be so high. But back to the point that I want to illustrate, even though the question was not related, velocity and friction are not coupled. Velocity is purely dictated by continuity. But what if there's friction that is such a long pipe that the friction is so dominating? Well, what happens is if you don't have enough pressure to overcome that length of friction loss, the flow will stop. And you don't have steady state problem. As soon as you tell me a steady state problem, I don't care how long the pipe is. What comes in must go out. That has to be very clearly articulated, because it's something you have to struggle with. Is that clear? Okay, so here is a very simple problem where the illustration is to show the difference between an idealized problem, low losses, versus what if I account for everything, friction and minor losses. I have a pumping system here that is 3/4 inch pipe, just like your household application. The flow rate, you are told, is about 12 gallons per minute. So do you have a feel for what is 12 gallons per minute? Do you know what is a 5-gallon bucket? A white 5-gallon bucket about this tall, about this diameter? That's 5 gallons. So fill 2 of those up in 1 minute, so 30 seconds per bucket. That's about very typical household garden application where you turn on the faucet and the flow coming out is about, turn out to be velocity for this 3/4 inch pipe is about roughly 10 feet per second. That's typically what you have in your house when you turn on the faucet in your kitchen or outside the garden. And what you are told then is to analyze this flow system, first assuming no friction, everything is inviscid, and then account for everything. All right, you understand the charge? At the exit, you have a faucet, a nozzle that actually has a smaller diameter, from 3/4 inch to a 1/2 inch. So there's some type of kinetic energy and velocity at the exit, and that's very typical of a household water supply. Any question on the statement of the problem? The length of the pipe is given, the change in elevation is given. Question is, how do I now calculate, based on this system, what is the pressure at the supply from the municipal that is sufficient to make sure it overcome all the losses, the change in elevation, and the exit higher velocity. All right, for 2 cases, ideal, inviscid, and accounting for everything. So let me see if I can lay them up directly below the flow system, so we can hope to use this to illustrate how all these components come into play. So if you look back at the exit, is the feed jet, what is the pressure at the exit of the water faucet? Atmospheric. So we all end up at atmospheric. And then working back is how I can determine what supply pressure is needed to push the water over all this plumbing at a flow rate of about 10 feet per second. And if the flow rate change, well, everything changes. Because the friction factor changed, the Reynolds number changed. Inviscid, low losses. Starting from here, this little nozzle, this valve here have no consequences. The only small drop here is that due to this P2 is 0 psi-G. So this sharp drop here is simply due to kinetic energy of 3/4 inch to a 1/2 inch nozzle. From that point on going to the right, which is through all of this, since we assume no losses, It's not a one-to-one correspondence, so I better be careful not to confuse you. The flow here represent all of this. If you have no losses, then the pressure remains the same, right? From here to here, I have what causes this pressure to change? Huh? Elevation, yeah, potential energy, and that's it, no friction. Again, a horizontal pipe in here, no change, constant, and then again, another section of gravity, and that's it. And then I'm to my source, where the pressure has to be, in order to drive the flow, pretending there's no losses. The pressure needed is very moderate, a little over 10, 11 psi, that's all. And that's enough to 1 water to 2/4 of elevation change. Do you see it? Now the next step then is now I need to account for both frictional, multi-diagram type losses plus the minor losses. So part of that is the same when I start from the nozzle, but now from this plumbing here, from this valve to the other valve, I have what determines the slope of where my finger is pointing. What constitutes this pressure drop along this section of the pipe, which is from here to here? Friction, only friction, nothing else. So this is purely from Woody diagram, where you know the friction factor by knowing the Reynolds number and the build of the pipe. 3/4 inch plumbing, you know the roughness. All right, it's only due to friction factor, and that determines the slope. This sudden drop is due to this valve, minor losses, no distance, sudden change, all due to force separation. Then on to the next one, which is this section. The slope is different versus that of this section. What is causing a steeper drop in pressure for this vertical section? Elevation plus friction, 2 pieces adding together, and that determines this slope, which is different than this slope. And continue on, those are minor losses of the turn. You can determine the slope, whether it's a vertical pipe or a horizontal pipe. Steeper pressure losses is gravity plus friction,